Hello students, welcome to our class Mechanics of Materials. Today we will continue our stress transformation. This is the lecture number 4 and this is the last lecture on stress transformation. Now in last class we learned how to draw a Mohr circles. So we draw a Mohr circle on an element which has a stress state of this type of, so 25 megapascal tension, 35 megapascal compression and 10 megapascal of shear stress. So this is our final Mohr circle base of these particulars. This is our final Mohr circle of this particular stress state, and these Mohr circles we have drawn using this stress state, and in today's class I will show you a slightly different way to draw the Mohr circles. So again we use the same element with the same stress state. So sigma x is here is 25 megapascal and it is tension, sigma y 35 megapascal, it is compression, and tau xy is 10 megapascal. Now so we will remember now to draw these Mohr circles we will identify two different points. So the point 1 is x coordinate of the point 1 is normal stress in the x direction, the normal stress in the x direction, and y coordinate of this point 1 is the shear stress. Similarly, point 2 is normal stress in y direction, this is sigma y, and the shear stress. Now let's find the point 1. The point 1, as I said before, point 1 is the normal stress in x direction. So this is my x direction, and this x phase, this sigma x 25 megapascal is outward from this x phase. That's why it is positive. If it goes inward, then we can write this 25 actually negative. And the another way to understand the positive or negative is to see whether it is a tension or compression. If this normal stress is tension, then it should be signed as positive. And now this 10 megapascal is my shear stress, and this shear stress actually creates a rotation. It rotates this x phase, this 10 megapascal in x phase rotates this element to anti-clockwise, and according to the sign convention, anti-clockwise is positive. So shear stress is positive, as I said before, because it creates anti-clockwise rotation. So the point 1, coordinate of the point 1 is 25 and 10. 25 and 10. So it is 25 because it is the normal stress in the x direction, and it is positive because this 25 megapascal is outward from this x, this is my x phase, and also it is also tension, so it's a positive, and 10 megapascal is the shear stress in x phase, and it rotates this element anti-clockwise, and according to the sign convention it is positive. Now consider the point 2. As I said before, point 2, the x coordinate of the point 2 is normal stress in y direction, and the y coordinate is the shear stress. Now this is my y phase, this is my y phase, and sigma y is 35, actually minus 35, and this is minus because is this 35 megapascal is inward from the y phase, it goes inward. And other way we can say this 35 megapascal actually compression, it compresses this element, so this 35 megapascal is negative. And here we have this y phase, there is a shear stress of 10 megapascal, and is 10 megapascal in y phase rotates these element clockwise, and shear stress causes the clockwise rotation is negative according to the sign convention. So the point 2, the coordinate of the point 2 is minus 35 and minus 10. It is minus 35 because it is the normal stress in y direction, and negative sign because this stress is directed to inward of the y phase, also it compresses the elements. Now so we will be drawing our Mohr circle of this stress state using this graph. Now in order to do that, we learn the point 1 and point 2. We draw the point 1. Here is the point 1. It is 25 and 10, and let me put this way. So this is my horizontal axis. This horizontal axis is stress, and this vertical axis is shear stress tau, and each grid in sigma axis is 5 megapascal. So this is 5, 10, 15, 20, 25, 30, 35, and similarly in this way minus 5 to all the way to minus 35, and sigma is positive, as we discussed in our last lecture. Sigma is positive to the right, sigma is positive to the right. From here to here it is positive, and from here to left it is negative, and the shear stress tau is positive downward, so it's a 5, 10, 15, 20, 25, 30, 35, and tau is negative upward. So we draw point 1. Our point 1, the coordinate of point 1 is 25 and 10, so that means horizontal component is 25 and vertical component is 10 plus 10. The other way says we can, the normal stress sigma component is 25, tau component is 10, and the point 2 is minus 35 and minus 10. So once we draw these 2 points, the next step is draw a line, connect these 2 points. When you connect these 2 points, actually it intersects the sigma axis at a certain point. It intersects sigma axis at a certain point, and this line is representative. Theta is equal to 0 degree. This line representing here theta is 0, and this is the line, this line where it intersects the sigma axis. This point, the intersected point, is the center of our Mohr's circle. So don't confuse with this point and center of coordinate. Center of coordinate might be the same as center of Mohr circles if the line goes, the line intersect at that point, but in our case the line intersects at actually minus 5 0. Now, so we got the 2 points, we got our center, and from here to here, from center to point 1, either from center to point 1 or either from center to point 2 is the radius of the circle. And the next step is simply draw the circle. So if you draw the circle, as you see, this blue circle is our Mohr circles, and these Mohr circles, as you noticed, it intersects the sigma axis in 2 different points, here and here. Okay. So this sigma 1, where it intersects the sigma 1 and sigma 2, sigma 1 and sigma 2 are principal stresses, and we can easily calculate the value of sigma 1 and sigma 2 by taking the distance from the origin, from this center of a coordinate. So if I take sigma 1, if I measure the distance from here to here, it is 26.5 megapascal. So principal stress, first principal stress is sigma 1 and its value is 26.5 megapascal. We can easily measure from this graph, and similarly we can measure the sigma 2, which is around minus 36.5, and to measure this we need to find the distance between this intersect point, between this intersect point from the center, and that is minus 36.5. Also this circle intersect in 2 different points of this tau axis. One position is here, the other position here. To find the maximum in plane shear stress, we just need to measure the distance of this intersection from this center. We can either measure this one, either this one or this one. That should be fine. Either one is be fine, and if you measure that, the stress is 31.5 megapascal. Now, so this system, the method I discussed today is pretty straightforward. You don't need to memorize any equations of principal stresses, maximum in plane shear stresses. All you need to know how to identify point 1 and point 2 and draw a circle based on this point 1 and point 2. And so all the equations we have discussed and the Mohr circle we discussed basically is valid for the plane stress, as I mentioned at the beginning of this stress transformation. I want to recap this plane stress concept. In the plane stress, basically instead of having all other stresses, we only consider two normal stresses, sigma y and sigma x, and one shear stress tau xy, and basically these shear stresses tau xy actually operate all the four planes here, 2, 3, 4, these four planes. And this plane stress we can actually we can give an example. If basically plane stress, all the formula I have showed you, Mohr circles and the stress transformation from the plane stress is valid, also valid for thin plate. For thin plate, this is an example of a thin plate. So the plane stress formula is valid for this kind of thin plane. Also, if it is a rod, if you want to measure the stress condition on the surface of this rod or tube, you can use the plane stress formula. There is another condition, another stress, another state which is known as plane strain. So plane strain is completely different from the plane stress, and all the equations I showed and the Mohr circles we drew is not valid for the plane strain. So consider a block which has two fixed support on perpendicular to the z direction, and if we apply load, compression load from the top and compression load from the side, what happens? There will be no elongation in z direction. That means your strain, normal strain in the z direction equal to 0, so does your shear strain zx and zy. So if a loading condition meets that epsilon z is equal to 0, gamma zx is equal to gamma zy is equal to 0, we can consider these loading condition as a plane strain. So plane strain, another example, a classical example, the plane strain is the bar of an infinite length. If this bar, if you compressed on from along the y direction and along the x direction, but the z direction is free, there is nothing in the d direction, you just think about that. This bar is not either elongated or contracted in the z direction. So this Ez is 0, so does gamma zx and gamma zy, and this is an example of plane strain. Now, like the plane stress, we measured principal stresses, we did the plane stress transformation. Actually, same thing we can done for the plane strain. So this is the strain transformation, and we can call, instead of stress transformation, we have to name it the strain transformation. So this is the equation on the left hand side. These are the equation of the stress transformation, and the right side the equations from the strain transformation. And the procedure for deriving or developing the strain transformation equation is pretty similar to the stress transformation equation, and the equations are look pretty identical. Just take a look at the stress transformation. So this is the stress transformation. This is the change of stress in the new orientation sigma x prime. You see sigma x plus sigma y by 2, sigma x minus sigma y by 2, cosine theta tau xy sine twice theta. This is the shear stress, right? Now look at this equation. Instead of sigma y, sigma x and sigma y, just replaced by epsilon x and epsilon y. And this is a shear stress, and this is actually shear strain. Only difference is that here the shear strain is half. That's the only difference. Even the shear stress is same. Only difference is that your shear strain is going to be half. And this is the equation of principal stress, sigma 1 2. And if you look at the only difference says are you need to replace your stress component with the corresponding strain component. Sigma x should be replaced by epsilon x, and so does sigma y and tau xy. Now, and this is the in plane maximum in plane shear stress and maximum in plane shear strain. All the equations are pretty identical. So try to understand the concept of the plane stress and plane strain, and for the sake of time I did not explain the plane strain transformations, but I hope if you look and study the plane stress transformation, you will be able to do the strain transformation. That's all for today. Please watch these lectures multiple times. This stress transformation is a very, very important concept of mechanics of materials, and so does the Mohr circles. So in your next one of the next courses, machine design, you will need these analyses, these transformation equations frequently. So try to understand those concepts and email me if you have any questions. Thank you very much. I hope all of you are healthy and well. Enjoy your time.